All right, this is a quick one this week on vacation. All right, so let's talk about the use of part stack elements inside LS-Dyna to model multi-layer structures with a single representative shell. So it is a card that is very convenient if you want to model a structure with, say, a ton of layers, and each layer has a different property. So it actually gets a lot more difficult to sort of represent that if you have to do a layer by layer assign part, mat, and section, and contact, and so on and so forth. So this specific functionality in Dyna allows you to do that very quickly, which is a very convenient way to do so, as I will demonstrate in this video here. Okay. All right, so the stack element essentially work with this kind of template, right? So for example, if you want to model a laminate glass with 3 different layers, the total layer thickness is say 4.5 millimeters or something like that, right? What you can do here is you can look at this part, assign a part ID to it. This 99 ID is the ID of the entire structure, right? Now each of these, but it is not a part ID. The part ID is still 1, 2, 3, but this is the part stack element ID that you want to have as part of the full model, and this is what's gonna get referenced later on. Okay, but within the laminated glass part ID 99, you're gonna have 3 different parts. Each of the part will have its own section, its own material, its own hourglass control, and then you also have its own thickness. Now, if it's a solid element, you can also define the number of solid element within that layer. So, for example, if you want a solid shell connection, you can define section 2 for shell, and then put section 1 here. You will have a solid shell connection in that stack, and that allows you to essentially define different material, different thickness, different layer, number of elements, all within a single functional material card template like I have here. Okay, that is the overall structure for how this card works. Now it's the specific implementation, right? So I can show it to you real quick. What I'm gonna do here is let's go ahead and open up this one right here. I'll let it open, then I'll explain. But basically, you can sort of see the basic idea is that the first layer of element, which is the actual geometry we import into the preprocessor, like you can see here, right? Like you can see here, this shell right here is the representative shell. It has a thickness that you define to be 0.25 millimeters, right? And then within here, you can define the 3 different layer thickness right here, 0.1, 0.05, 0.1. And together it adds to 2.5, which is the actual layer, 0.25, which is the actual thickness of this layer. Now it doesn't matter what the actual thickness is, or it doesn't matter what kind of material assigned here. We're gonna delete the call out for this component, and we're gonna rely on the keyword template to define the stack behavior, and that's essentially how it works, right? And then this thing can be done for more than just a single layer of simple geometry. You can be done for much more complicated geometry, such as a cylinder, such as a wave structure, right? And the way it does that is that the layer itself is automatically generated in the model, right? So he's gonna look at a specific logic based on the representative shell layer, and he's gonna generate the stack based on that center layer to be the mid layer, and the shell thickness as you define in the keywords. Okay, and the way it defines the shell thickness is based on essentially this rule that I copy pasted from the documentation. It's slightly confusing, but basically, it's essentially following like an averaging type of logic is essentially what it's doing. The total thickness is the total thickness, plus t minus t and half, right? That's the total thickness. And then depending on the individual layer thickness and whether or not it's a solid to solid or solid to shell, it's gonna have a slightly different logic. But basically, what essentially this says is that if the top layer is a shell, this offset will go all the way into the mid surface of the shell. You can't have a gap in the stack. Is essentially what it's saying, right? Which is why this method makes makes it really difficult to do a solid shell stack, because you have to basically offset the solid layer to the shell elements, unless you are using the offset not from middle, which is not something that I'm a fan of. I usually don't like to do the model with the shell elements not being centrally offset, right? So I don't like to offset to one end. It makes stress reading very difficult, less reliable. which is why my opinion is that we don't want to use this for shell, solid shell, but you can still do that if you're careful and know what you're doing. Okay, so first example here is a shell stack, as you can see in the model, right? I have a section shell assigned to all three parts, and we can sort of see here the result is I have 3 layers of shell, and this is the end result after I started the model, right? You can see 3 different layers of shell all stacked on top of each other. Now the problem with this method is that there is no contact between each of these shell layers. So what you will have to do is to define a tight contact card between each of these layers, and we have to have a very small amount of offset, like you see here. And when you do that, what you have is if there's no contact, you can sort of see it just sort of overlap each other. You can sort of see the green star on top, and it went below the red, right? So because there's no contact between the 3 layers. Now, if you were to use the contact card like I showed earlier in the previous step, you can sort of see the contact is now established between the 3 layers, and so you sort of have a composite of 3 different shell material. This is actually really easy to do if you think about it, because all you have to do is to import a single shell body, like right here, right? And the rest of it, you can import a keyword template, and all 3 stack is going to behave as a monolithic body with a tight contact between them, but they are going to have a different property across the elements, right? That is a very awesome thing to have with a single keyword template and a single shell body to define it. Okay, now the best way, in my opinion, to do this is to use 3 different solid elements. So section 1 is a section solid. So if you use 3 different section solid use 3 different solid layers, you can define the number of elements across each layer, and you can define the thickness across each layer. So in this case, I have a 0.1, 0.05, and 0.1 layer. Each layer has 2 solid elements, and in this case, the contact is perfectly no merged, right? It's very much like you are importing this one by one yourself. Now you might ask, what are the benefits? Why not just do it by hand? But imagine if you had to do 10 of these, 20 of these, and so on and so forth. It becomes a lot more error prone and time consuming. And using this method makes it really easy to handle this kind of geometry. And the part stack elements can also be done for other shapes like a cylinder. So you can sort of see here, I have a default cylinder that starts with this kind of geometry, nothing but a shell. Right, I can define the shell thickness whatever I want, and then I can look at the stack elements. The stack element is going to have a 10, 5, 10 stack thickness. Each stack going to have 2 solid elements, right? And in this case, you can sort of see, or in this case, I think I had 3, but regardless, you can sort of see in this case, I have a very clean 3-layer stack offset from the representative shell elements, right? And you can do this for other more complex geometry. Based on my understanding and my reading, there's not a lot of limitations. As long as you can find the mid layer, you just does a geometric offset, just like the way you would do it with the shell elements. Okay, so as long as it is a shell body, right, that you can mid-surface, you should be able to use this technology to generate multiple layers of solids and shells and solid shells, whatever you want. Okay. Now, and you can sort of see if you have a really thick layer with 10 different layers, right? You can sort of see this is a 10 different layer. Each of them has 3 different layers. This right here will be a lot more difficult to do by hand. But in this case, all you have to do is importing a single shell body, a single shell representative shell. Make sure the thickness corresponds to the overall thickness. Then just assign the thickness to each layer, assign the material to each layer, assign a section, assign an hourglass. And you will have a full stack that allow you to do other analysis with, and it's all no merged, very cleanly done. It makes the job cheaper to run. It's also extremely efficient in terms of getting the model to solve quickly. Okay, so this is a very useful thing for a solid stack and a shell stack with contact. Now, what is less effective, in my opinion, is if you have to do, say, for example, a solid shell solid stack. So this is a solid shell stack. As you can see, right, by making the offset in the middle, the way the solid piece is going to go to the mid-surface area of the shell, so it's not going to actually do a really good job of, you can sort of see, right, this is a mid-surface, this is the mid-surface, and the middle part, which is a solid element, is going to basically align with the mid-surface, right? So this is not what we want. This intersection is not acceptable. But if you do a different kind of offset, it doesn't always behave very well. Like in this case, I tested with an offset of -1. You can see it also doesn't do a really good job. I did an offset of +1. You can also see it didn't do a very good job. right? So there might be ways to get this to work, but it's really not consistent. You have to find your shell normals, and based on the documentation, it only works when it's the uppermost layer of the shell being shell body, which means if you have a 10 layer structure like this and you want to make one of the middle ones a shell, it doesn't do a very good job, right? So the best bet is to try to use solid elements as much as possible, or use shell elements with contact. I think it does a very good job with this card. Using a mixed body of shells and solid doesn't do a very good job, especially because, you know, if you think about it, shells has 6 degrees of freedom, whereas solids only has 3. So it becomes very confusing to think about what it means to actually no merge them, right? Because it's not exactly working the way you think it does in a lot of ways. And if you use tight contact, you can't use constrained tight contact. You have use springs, use penalty-based contact. So a lot of that is not very clear on how that's done. So my opinion is that let's not use a mix of shell and solid in the part stack elements. But once you do that, everything else does a great job, as you can see, right? So I can basically generate, all I have to do is import one of these, and then do a basic setup. I have my keyword template imported here. This means nothing in here, but once you solve this, right, when I export this model, it's gonna look like it's have a single layer of element. But when you start the LS-Dyna run, what's actually being processed, what's actually auto-generated is the shell that you're seeing here. Right, so shell like these are auto-generated at the start of the transient analysis. Right, so once you have the part stack element card in the input file, it will automatically generate this stack of elements once you start analysis, and it actually solves very quickly in a situation where otherwise it wouldn't have solved very quickly. Right, so it's both an efficiency boost and a convenience boost in terms of setup. So I certainly believe there's a lot of really good application for this keyword, for this functionality that we want to pay attention to, especially if you are modeling some type of a composite material, composite model. It has a very convenient way to allow you to handle extremely thin layers without having a problem. Okay, thank you very much.